So let's look at the renal corpuscle and what is going on here. What is happening here? Okay. Again, we're looking at urine formation. We're going to be looking at step 1, step 2, and step 3. Okay. The one thing I want you to remember is that if it is in any of this vasculature, it is within the body. Okay. So if it's in the vasculature, water, sodium, urine, chloride ions, any of the things that I tell you to pay attention to, if substance is in the vasculature, it's in the body. Okay. So if the substance that we're talking about is in the afferent arteriole, in the glomerulus, in the efferent arteriole, in the peritubular capillary, in the vasa recta, okay, if it's in any of that vasculature associated here with the nephron, it is in the body. Use a different color here. If the substance is in the tubular network, ULAR, it is waste. Okay. So if the substance is in the tubular network here of the nephron, okay, if it's in the capsular space or in the proximal convoluted tubule, nephron loop, distal convoluted tubule, or collecting duct, it is out of the body. So we are going to see it as waste. Okay, or our body sees it as waste. Okay. Now, stuff's going to happen here, and it's going to force damn near everything out. Is it waste automatically? No. Because if we force everything out, or the vast, like 98% of it out, okay? So let's say I push out all my sodium. Let's say I push out chloride ions. Let's say I push out calcium. Let's say I push out individual amino acids. Whatever gets pushed out, those levels are going to drop within the body. How does the body determine that? Chemoreceptors, right? So as soon as these levels get pushed out here in the glomerulus, and this is just an overview, we'll dive into all the parts and pieces here to bore you to death. But as soon as we push it out into that glomerular capsule, it's not in the body anymore. Those levels are going to drop within the body. The body senses that. It's like, you know what? I pushed everything out because of forces that we'll talk about here in a second. But then it's going to be like, you know what? I really need that chloride ion. I really need that sodium ion. I really need all that crap that I pushed out. I don't need to get rid of it. So we're going to reabsorb glucose. Okay. So it's going to reabsorb all that stuff. And the vast majority of reabsorption occurs right here. Then we just spend the rest of the structures here going down the nephron loop and then distal convoluted tubule and the collecting duct of just refining that. Okay. So when we move these substances back into the blood, that is reabsorption. Back into the blood. Okay. That's going to be reabsorption. So it's going from the tubular structures into the blood, into the vasculature. Secretion from the blood into the tubes. Into the tubes. Okay. So our three basic steps, 1, 2, and 3. 1 happens with only in the glomerulus. Tubular reabsorption can occur through any of the tubes, proximal convoluted tubule, distal convoluted tubule, collecting duct, nephron loop. Okay, it can occur in anything that has a tube in its name. Vast majority of reabsorption occurs within the PCT. Step 3, when we reabsorb it back into the body, the levels will rise back up, and you'll read the situation back. You know what? I don't need X amount. And so it will secrete some of that we just reabsorbed back into the tubular structures. And once it's in the collecting duct, it's PP, it's urine, and it's going into the toilet. Okay. So that's the basic gist of what's happening here. So let's look at some of this anatomy really close up here when it comes to affecting glomerular filtration, because that is the first step that we have in urine formation, and all of glomerular filtration happens within that renal corpuscle in the glomerulus. Okay. When we get up close and personal and look at that glomerulus, here's what it looks like. Okay. We have a number of stuff here. We have some fenestrated capillaries. And then around that, we'll have these things called podocytes. Cyte means cell. Poda just means it has a foot-like extension that extends off of the cell body and wraps around the capillary. We also just have the basic kind of parts and pieces of the capillary there. We have a basement membrane. Okay. So we have all of these various different layers that are going to be found wrapping around that glomerulus. It's actually pretty complex. All three of these things are going to help influence what can be pushed across. Okay. And when I mean pushed across from inside of the capillary here, pushed across all of these layers that we'll see here in a second, in another view, into that little space here. Okay. Into this space here. It's this unique setup that ensures big things don't go across. Okay. Large proteins cannot go through. Okay. Cannot go through. One, they're not big enough, or I'm sorry, the holes within the glomerulus are not big enough. The spaces within the within these feet-like extensions. Okay. Here's the podocyte. This whole thing's the podocyte. Here's a little pseudopodia that's coming out, that little foot-like extension. These are tiny little pedicles. Okay. Think of them as the toes. And we can have a little bitty space in between it. That little bitty space is not too big at all. Right? So big things can't get across this. Proteins. Okay. Now, individual amino acids can get across that, but a lot of individual amino acids aren't that big. But when you get 10, 20, 30, 40 of these strung together, now you start to get in size, and that's going to help prevent them going across. Red blood cells can't get across this thing because of the size, because of these three different layers. If you do see if you do see blood in your urine, if you do see red blood cells, then you know there's some kind of inflammatory event occurring here within the nephron. How do you know it? Red blood cells can't get across unless there's an excessive amount of swelling and inflammation occurring within the kidney, if there's damage to these nephrons, then these slits get bigger. Then these holes get bigger. Now there's space that exists for red blood cells to be pushed through. And that's not a good thing. And it's usually associated with, strep infections. But it can be as simple, guys, as you going on a long run and then going to, do a blood test. Okay, do a urinalysis. Okay. If you are an individual and you do a lot of running, it is perfectly normal to have a little bit of blood in your urine. You're running at a pretty decent pace, bouncing up and down. Let's say you're running for 30 minutes, 45 minutes, an hour. I mean, that's a lot of wear and tear, okay, just from the normal wear and tear of bouncing around and running. So to have a little bit of blood in that situation, it's going to be normal, okay? If you're just sitting around doing nothing, fighting off an infection, go and they suspect something, so they do a urinalysis and then they find blood in there, that is not normal, okay? So with that caveat, I'm working with not normal. You not going out and running a half marathon before giving blood or having a fitness exam done on you for life insurance policy, because that can happen. All right. So when we look at, excuse me, when we look at this thing in cross section right here, you can kind of see it. Okay. Here's the glomerulus right here. This is the capillary. There's the endothelium of that capillary. Here's the basement membrane. And this is going to be the podocyte. These are those pedicles right there. And there's your little slit in between those pedicles. Okay. So you can see we have a number of layers here that really really prevent those large proteins from getting across very easily. Small little amino acids, they can generally get across. Big stuff can't. White blood cells, well, they ain't getting through. Okay. Red blood cells, they're big, they ain't getting through. Okay. It's only stuff that can get through that plasma membrane, get through those small little openings that can get across. So we have three different things. We have the endothelium of the glomerulus. Okay, we have just those small fenestrations, those small little openings there to allow small water-soluble substances to come through. We have the basement membrane of the glomerulus that helps to restrict large things. And we have our podocytes. Okay. Which are helping to form filtration slits. Okay. That can allow some small proteins to get through, but not all of them. Okay. Water-soluble stuff gets through. Glucose, urea, ions, sodium, chloride, calcium, potassium, bicarbonate, vitamins B and C, the water-soluble vitamins, okay, ketones. All of these can get through the filtration slits, through the basement membrane of the glomerulus, and through the fenestrations of the glomerulus itself. This is blood. Okay. This is blood. In it are our formed elements and our water component plasma, right? As soon as we push water out, as soon as we push some of that water-soluble stuff out of the glomerulus and into that capsular space, we give it another name. That name is filtrate. Okay. Oh God, what's going on? Filtered plasma with some solutes and a little bit of protein. Okay. This is what enters into that capsular space. Okay. Into that capsular space. All right. But it's called filtrate. I did not ask. Okay. I did not ask how many liters is produced. Okay. You produce a ton of filtrate, as you can see there, 180 liters, but you only urinate out like maybe 1.5, 2 liters. Okay. So you're pushing out a hell of a lot of stuff. Okay. You're pushing out a heck of a lot of water out of this glomerulus into that capsular space. You're pushing a hell of a lot out of solutes, water-soluble substances, glucose, water, amino acids, ions. Okay, there's a lot that gets pushed out here. All right. So even though I'm not going to ask you the number, the amount of filtrate formed, 180 liters, that's a hell of a lot of liters. If we didn't reabsorb this stuff, you'd be peeing all day. You'd spend the entire day in the bathroom urinating. And that probably doesn't sound a whole hell of a lot of fun. Okay. So the stuff that freely comes across here, free. Okay. The freely movable, freely moving in. Okay. What freely moves in? Excuse me. Goodness gracious. Water. Glucose. G-L-U. G-L-U. Glucose. Individual amino acids. And ions. Okay. That is what is freely moving across. Okay. Formed elements, large proteins. They do not come across. Okay. So large things do not come across. There's more than just large and small proteins. There's some intermediate sized proteins. Some of those can come across. It just depends on their charge. We didn't get into all the nuances of the 20 different amino acids. So understanding positive and negative charges, you don't need to worry about. Okay. It's either big or it's small. Don't worry about the in-between stuff. Okay. We do have these things called mesangial cells. Okay. We saw them on the outside when we looked at that juxtaglomerular apparatus. There are a few mesangial cells on the inside as well. And so they can act as a phagocytizer. So if there's something in the blood or something in the filtrate that shouldn't be there, it can phagocytize them. The mesangial cells that you find outside of the glomerulus in that juxtaglomerular apparatus and inside, they can influence one another. And we'll mention that briefly in a little bit with ways that we can regulate your information. Okay. So we are in the glomerulus and we get pushed out of the glomerulus. And when we get pushed out of the glomerulus, we're no longer called plasma. We are called filtrate. Okay. We are called filtrate. What's in the filtrate? Anything that can freely move across. Water, glucose, small amino acids, ions. What can't come across? Large stuff. Okay. Formed elements, large proteins, those cannot come across. If you find them in there, you know something's wrong. Just like we have pressures causing all of this stuff to be pushed out within a capillary bed, we have the same thing here as well. Okay. The most important of the three is glomerular hydrostatic pressure. This is basically blood pressure within the glomerulus. That's what it is. Okay. Because remember, the glomerulus is vasculature. So this is the body. So this is the force exerted on the wall of that fenestrated little structure there by the body, your blood pressure. Okay. And it's high. Okay. This pressure is higher than the other two. The other two are not as high. Together, collectively, okay, they can help counterbalance it a little bit, but individually, they're smaller. I'm not going to have you know their numbers because you don't need to figure out glomerular hydrostatic pressure. I'm not having you figure out the calculation for net filtration rate, okay, or glomerular filtration rate. I'm not having you do any math on this thing, all right? So what is glomerular hydrostatic pressure? It's the pressure in the glomerulus, okay? And this is what's doing the pushing, okay? Pushing the water out, okay? Pushing the solutes out. This is the force that does it, all right? Where is it going? Into the capsular space. Glomerular hydrostatic pressure is higher than blood pressure. Why is it higher than blood pressure? Well, we have a large diameter of an afferent arteriole going in and a small diameter of an efferent arteriole leading away from it. So if you have a whole hell of a lot of fluid coming in on one end, but a very small tube for allowing all that fluid to exit, it creates a pressure within that glomerulus. Okay? And it's that anatomical difference that sets up this larger glomerular hydrostatic pressure. I need this pressure to be great. Okay? I need this pressure to be great. If I don't have a huge amount of pressure here, filtration cannot occur. Okay? Filtration cannot occur. So if blood pressure drops dramatically, you can't form urine. Okay? If blood pressure drops dramatically, you can't form urine. You can't get rid of waste. Obviously, this is going to affect pH. It's going to affect the body's ability to properly drop off and pick up oxygen, carbon dioxide, bicarbonate ions, all that freaking nonsense that we talked about earlier. Okay. So helping to maintain a constant blood pressure is important. Okay. Helping to maintain this constant higher pressure here within the glomerulus is ultimately important in terms of forming urine, getting rid of metabolic waste. Here are the other two forces. One of these you can probably already figure out, and I hope it's this one. Okay. Remember, God dang it, I don't know why it's doing that a lot today. This is drawing the fluid back into the glomerulus. Remember, this is that sucking phenomena because of those large proteins within the blood. Capsular hydrostatic pressure is the pressure in the glomerular capsule. And I mean, here they are. I mean, there is the capsular hydrostatic pressure. You can see it's, not very big compared to the hydrostatic pressure in the glomerulus. All right. Not very big at all. Okay. Really small. So it's not a huge force. But that colloid osmotic pressure, that sucking phenomena that those proteins that stay behind cause is pretty significant. Okay. And I did not ask any of these on the exam. Did not ask any of these numbers on the exam. I don't even think I asked what the normal pressure is at all here. Okay. But it's these three forces that help to ensure that filtration occurs. Okay. Which one can the body regulate a whole heck of a lot of? This one right here. Okay. That one I can affect more than any of these. How? By magic. And we'll see that magic. Okay. And we'll see that magic here in a second. Okay. Capsular hydrostatic pressure impedes movement of additional fluid. So When would capsular hydrostatic pressure be significant? It would be significant if blood pressure was very low and we didn't have enough force coming into the glomerulus at all. Okay, so if we didn't have if we had an excessively low blood pressure, okay, and there wasn't enough blood flow going into the glomerulus, capsular hydrostatic pressure could ultimately be too much for that to happen. And then filtration doesn't occur, and then you get into an acidosis type state, and that's not very good. Okay. So these are the three forces. Okay. One is great, glomerular hydrostatic pressure. The other two collectively are good. I mean, high together. Individually, not very big. Okay. Capsular hydrostatic pressure is generally minimal. And when everything's normal, that small amount of force of the filtrate does not influence a whole hell of a lot. The only way capsular hydrostatic pressure comes into play is if you have excessively low blood pressure. Of the two that oppose the glomerular hydrostatic pressure, blood colloid osmotic pressure is going to be the big one. Why? Large proteins don't get through that filtration membrane. They stay in the blood. So they're going to exert a huge force, okay, as they did within the capillaries that we saw in tissues when we looked at how fluid moved via that bulk movement. Okay. The difference between all those is net filtration pressure, and to be honest, I really don't think I asked any questions on it. Something that I did ask a number of potential multiple choice questions on. Is glomerular filtration rate. What is it? That is what it is. Okay. It's usually determined by a minute time. It's a volume of filtrate formed per minute. Glomerular filtration rate ensures that I get rid and form a proper amount of urine. If I produce a consistent amount of urine, I am maintaining blood volume. And by maintaining blood volume, what am I helping to maintain in the body? Can anybody venture a guess? Blood volume equals blood pressure. So if I have a higher amount of water inside my system being reabsorbed, I want to get rid of that. To maintain that normal blood volume, to maintain that normal blood pressure, I need to have a glomerular filtration rate that accommodates that. Okay. So it's going to increase my urine output. So glomerular filtration rate can be affected by water. Can also be affected by certain solutes. And really the big one is salt. And that's one of the ones that you probably will have to know about. So if I have increased water, if I have increased salt within the body, that's going to increase urine output, which can help to maintain a consistent blood pressure. Okay. This was that other arm of blood pressure that we made reference to when we looked at the cardiovascular unit. This is the kidney component of it all. There are a number of ways that I can affect glomerular filtration rate. I can affect glomerular filtration rate by affecting how much blood comes into that glomerulus. I can affect that. Those afferent arterioles, there's smooth muscle within them. Okay. So I can affect how much blood goes in there by affecting that smooth muscle. And I can affect glomerular filtration rate because of that. By either increasing the GFR or decreasing the GFR by affecting that smooth muscle. I can affect it by how much salt do I have in the system. We have special cells that detect salt levels. The kidney can monitor this. Extracellular components can monitor this and release some of those hormones that we made reference to when we talked about regulating blood pressure. We'll see them here again. Because not only did they affect the blood vessels, they're also going to affect the anatomy down here as well. So there are a number of variables that can affect this rate of glomerular filtration. There are two of them that are occurring within the kidney itself. And we're going to call these intrinsic controls. Now, depending upon the book, they can either be called renal autoregulation or intrinsic controls. It's the same thing. Okay? This textbook puts them both in the same boat. They call it renal autoregulation or intrinsic controls. Okay? Intrinsic is when the kidney does its own work in-house. Kidney is going to maintain, okay, a constant BP and GFR, glomerular filtration rate. We have two mechanisms. One, myogenic. When you see myo, what do you suggest or what do you think is being influenced? Anybody?
Muscle?
Mm-hmm. When you see myo, you always think muscle, right? So there's your smooth muscle. I'm just going to shorthand it SM, smooth muscle. Okay. This is going to be that afferent arteriole that we affect. Okay, because who brings the blood ultimately to the glomerulus? The afferent arteriole. And then we have a tubuloglomerular feedback. Okay. This is specialized cells that are detecting sodium chloride, NaCl. Okay. Salts. So these are my two intrinsic controls. Extrinsic is just hormones. Okay. Extrinsic is hormones. But these two here are the intrinsic control mechanisms. When it comes to controlling GFR, it's the first one that predominates. Okay. Oops, where's my thing? There it is. With the myogenic response, we are again affecting that smooth muscle like I talked about. Specifically the afferent arteriole. Okay. Only the afferent arteriole. Oh, excuse me. Efferent arteriole, we're not really affecting. Okay. we're more concerned about the afferent arterial because that's the blood coming in. Okay. That's where the blood is coming from. So that's what we're talking about here, is affecting that individual part. Okay. So if we have normal blood pressure, okay, there's my afferent arterial, here's the glomerulus, and blood's going in, backup of blood occurring because of the smaller size, and we create a normal glomerular hydrostatic pressure within there, and ta-da, nothing's really different. When we have a decrease in blood pressure, remember we are having less stretch. Okay. Now, when we talked about it out in the systemic blood vessels, okay, if there was a decrease in stretch, well, we just vasoconstricted, right? To increase that blood pushing on the walls of the blood vessels. This is different. This is opposite, okay? If we have a decreased amount of blood, okay, we have decreased stretch here, okay, decreased stretch. The only way that I can maintain a constant GFR, okay, because I have to maintain a constant glomerular filtration rate. I have to maintain a constant GFR to ensure that my blood pressure stays constant. If I get these wacky hills and valleys when it comes to GFR, then I'm going to have wacky hills and valleys when it comes to blood pressure. And that wouldn't be very conducive. I want to maintain a constant blood pressure. So if I have decreased blood pressure, okay, the only way we can do it and maintain that GFR is to relax that smooth muscle. If we relax that smooth muscle, it dilates. By dilating, I'm bringing in more blood into that glomerulus. Okay. This helps to maintain a constant GFR. Conversely, if blood pressure is increased, there's more stretch. So I need those vessels to constrict there instead of relaxing. Okay. And this is going to maintain that normal GFR. Compensates for greater systemic pressure, and I can maintain a constant GFR. So the myogenic response, in terms of normal GFR, it is the primary one. Okay. It is the primary one. This is the one that's working in terms of pressure being exerted on the walls. How much blood flow is coming into that glomerulus? If it is too little, vasodilate. Okay. This allows more blood into the glomerulus so I can maintain those pressures, especially that glomerular hydrostatic pressure. This allows that 180 liters to get forced out and through magic, reabsorb the most of it and only produce a normal 2 liters of urine. That sounds very short term, and it is. Okay. We have another system that can help regulate GFR, and that's that tubuloglomerular. And as you can see from the text there, it is the backup system. The tubuloglomerular feedback mechanism is involved with NaCl. So we have one involved with forces, and we have one involved with sodium. If there's high sodium, there's going to be high water. Okay. If there's a high amount of sodium, there's going to be a lot of water that follows it. Okay. This is detected by those macula densa cells. I am maintaining this GFR so I can maintain a normal amount of urine formed. Okay. That is the ultimate control. That is the ultimate reason to control this GFR. If I produce too much urine, then that could affect the volume of blood because there's less urine. That can affect other mechanisms outside of the kidneys. If mean arterial pressure drops excessively low, then that capsular hydrostatic pressure is greater than the glomerular hydrostatic pressure. And there is an insignificant amount of force to push all that solute out and form that filtrate. So if I don't maintain that proper amount of filtrate being produced, i.e. 180 liters, okay, then I don't ensure a proper amount of urine production. And if I get outside of that mean arterial pressure, okay, that MAP, then this can affect these various different mechanisms for a much longer period of time. With this tubular-glomerular feedback, it's a more chronically associated high blood pressure situation. Okay. I guess really intermediate. The myogenic response, that's the one that's primarily working all the time. So as blood pressure changes, as you start to become more active or move around, it's the myogenic response that is doing all the heavy lifting. With higher blood pressure, usually is associated with a higher consumption of sodium. And so this is where we get the tubulo-glomerular feedback. These are in those macula densa cells, right? These are in those cells that are within the distal convoluted tubule, right where the afferent arteriole enters into the glomerulus. So if I have a high amount of sodium found within that distal convoluted tubule, this is urine. This is going to be leaving the body. Okay. And so the body's like, we have too much urine formation here. I have too much sodium within my DCT. And because I have too much sodium there, I have too much water there. So I'm forming more than my 2 liters of normal urine. The body's like, I need to slow that down. So this tubulo-glomerular feedback mechanism is what kicks in when sodium consumption starts to kind of kick up. That causes constriction of that afferent arteriole, which slows down fluid movement or blood movement, I guess I should say, into the glomerulus. And that helps to lower your glomerular filtration rate, forming a normal amount of urine and helping to maintain a normal blood volume within the system. Can this be affected by what you eat? Hell yeah. Okay. Can this be affected by situations? Hell yeah. If you're outside running around on a very hot day, you're going to have a huge amount of loss of sodium ions through both sweat. Okay. And so the body's going to want to try to regulate that. And it does that. This is going to be the mechanism that is basically telling the body that, hey, I can't do this alone anymore. I need some help. And so this is where we're going to get hormones involved. So this tubular glomerular feedback mechanism is the backup to the myogenic. Myogenic is what's happening all the time. It affects the smooth muscle of the afferent arteriole directly. The backup, let's say, it's doing its thing. Got a lot of sodium in the system. A lot of sodium gets filtered out. A lot of water flows with it. We're producing a lot more urine. Body's like, damn, I can't keep this up. Macula densa cells sense it, cause the afferent arteriole to contract, slowing down blood flow into the glomerulus and slowing down that glomerular filtration rate. So I can maintain a normal amount of urine formation. If this can't do it, then that's when we get hormones. Okay. This is where we get hormones. Okay. One major hormone acts here on the glomerulus. There are some other hormones that act in another location. Okay, in the distal convoluted tubule and the collecting duct. All right. So there are a number of hormonal controls that are considered extrinsic. All right. The only one that affects this piece of anatomy, I believe, is on the next slide. ANP, atrial natriuretic peptide. The nervous system is also based outside of the kidneys. I know, shocking. During exercise or an emergency, but during exercise, that's one of the questions I believe on the exam. Okay. Because what's happening when you exercise? Blood is shifting, right? Blood is shifting from the reservoirs, the venous side of the system. We're shuttling more of that blood through vasoconstriction, right? And we're getting more blood now out of the venous side and into the arterial side. But where is all that blood going? It's going to skeletal muscles that are doing all this work, exercise. As we are shifting blood to other places that need it, we have less blood going to the digestive system. We have less blood going to the kidneys. So I want to maintain a constant, regular amount of glomerular filtration, constant, consistent amount of urine formation to help maintain a constant, consistent blood pressure, ensuring I can get blood to the brain during exercise and to all the skeletal muscles around during exercise. So sympathetics going to kick in, and we are going to get vasoconstriction of the afferent arteriole and of the efferent arteriole. And here you can see we are affecting both, not just the one. Why are we affecting both here? Because the amount of blood flow into the kidneys starts to drop pretty considerably during exercise or during emergency. Think of hemorrhaging blood. Okay, but I asked during exercise, I believe, on the exam. By decreasing that GFR, I can maintain normal urine formation. So I can maintain normal blood flow throughout the system. Sympathetics will affect granular cells of that juxtaglomerular apparatus. Produces renin. Renin did a whole bunch of stuff outside of the system, right? It was a potent vasoconstrictor. It stimulates the thirst center, which when you're exercising, you get more thirsty, right? It also stimulated the release of the angiotensin system. Okay, right here, I'm going to put a blue dot. That's where we had our mesangial cells. Kind of phagocytic in nature. Okay. There's a tiny little bitty microscopic space that exists there between that afferent and efferent arteriole. These mesangial cells kind of extend in here on the inside, and then we have some mesangial cells in there as well. And so we have these mesangial cells kind of scattered around here as well. Okay, it does a good job of kind of showing them off there for you. Okay. Put some dots on them. Okay. That angiotensin 2 helped the kidneys to conserve water. How does it actually do that? Well, it causes those mesangial cells, which were more phagocytic in nature as a function that we saw, but it causes them to constrict. When they constrict, that decreases the size of the glomerulus. If I decrease the size of the glomerulus, I decrease the glomerular filtration rate. There's just less holes for fluid to be forced through now. This allows us to conserve water. You're sweating. You're losing a lot of blood, or I'm losing a lot of blood, losing a lot of water through sweat. It's going to cause that blood volume to start to diminish. So I got to conserve it. Have to conserve that water so I can help to maintain a normal blood volume. So I can help to maintain a normal blood pressure, which is now higher, that is occurring during exercise. And I want to decrease the GFR to maintain that stuff. So there's renin. Renin getting stimulated to be secreted by that sympathetic response. The only hormone that we have here affecting it from the outside, aside from renin, but renin does, vasoconstriction, stimulates thirst centers. It does a number of other things. ANP is the big one here, okay? And I think there's a handful of multiple choice or potential multiple choice questions on the exam asking about what does this hormone do to affect GFR. Remember, ANP was released by the cardiac cells. Specifically, it's the atrial cells that are being secreted, that are causing this secretion to occur. When more blood comes back, there is a greater stretch on the atria. There's a greater amount of blood volume. There's a greater amount of blood coming back to the atria. When they get too much, because remember, we can only stretch so much there, right, in that heart. So when we start to get too much of a stretch occurring within the atria, this is when those cardiac cells will secrete atrial natriuretic peptide. Too much volume of blood. So I want to increase GFR to get rid of that excess blood volume, water volume. So here we get relaxation of that afferent arteriole, right? So we get more blood going in there. More blood going in there, I can form more filtration, more filtrate, sorry. I can have more filtration. I can form more filtrate. We relax those mesangial cells. Everything that we saw in the last one there with sympathetic is the exact opposite here. So just tell yourself that. Relaxes the mesangial cells, ANP. Increases the filtrate that can be made. Inhibits renin. And renin is what caused those suckers to relax in the first place. With increased GFR, I could increase my urine output. Blood volume will drop, and that means blood pressure drops with it. ANP, who secretes it? Cardiac cells in the atria. What does it do? It helps to increase glomerular filtration rate, to produce more urine, to help lower blood volume and therefore lower blood pressure. How does it do that? Inhibits renin, which causes relaxation of those mesangial cells. And it helps to relax the afferent arteriole, which helps to bring more blood volume into the glomerulus to ultimately form more filtrate, form more urine, again, causing that decrease in blood pressure and decrease in blood volume. Let's take a break. Okay. Let's take a little break. If you have any questions, please type them into the box. All this talk about your information. I've got to go pee now. All right. So 41, come back. 1051, come on back, and we will kick in to the next step.